Section 4.1 deals with first derivative and graphs. So what we're going to learn today is what the first derivative tells us about the graph of a function. So before we start with that, let's just recall what it means to be increasing and decreasing. So we say that a function, and we're going to call that function f, is increasing on an interval if from left to right the graph is going up. So what this is saying is for every two numbers x1 and x2 in an interval ab, the y value of f of x1 is smaller than the y value of f of x2. And that only happens if you're going up from left to right. And we also say that a function is decreasing on some interval if from left to right the function is going down. So technically it's for every two numbers x sub 1 and x sub 2 in that interval AB, the function's value at x sub 1, or that y value, is bigger than the function's value of x sub 2. And then for both of those, it's where x sub 1 is smaller than x sub 2. So what we really need to remember is that from left to right, if you're going up, your function is increasing. From left to right, if your function is going down, you are decreasing. So let's determine the intervals of increasing and decreasing for the following two pictures here. For the graph on the left, I am going to be decreasing from negative infinity all the way to positive 2. So I'm decreasing from negative infinity to positive 2, and I'm going to be increasing from 2 to positive infinity because the graph goes up from left to right there. For this next function, we can see that I am increasing from negative infinity to negative 2. I am decreasing from negative 2 all the way to positive 4. And I'm increasing again from 4 to positive infinity. So again, a function is increasing when it's going up from left to right, and a function is decreasing when it's going down from left to right. We can use the first derivative to determine where a function is increasing and decreasing. We say the following: if the value of the first derivative is greater than 0 for every value of x in the interval ab, then the function is increasing on that interval. What does that mean? Well, that means that since this function is increasing from the interval from 2 to infinity, that the value of the first derivative, f prime of x, in that interval would be greater than 0. Over here, same things, since this function is increasing from negative infinity to negative 2, and again from 4 to infinity, that since it's increasing in this interval, that the value of the first derivative for both of those intervals would be greater than 0. Also, if the value of the first derivative is negative or less than 0 for every x in the interval ab, then the function itself is decreasing on that interval. So what that means for us is that since this function was decreasing from negative infinity to 2, the value of the first derivative in that interval would be less than 0. Same thing over here, since we were decreasing from negative 2 to 4, then the value of the first derivative in that interval, f prime of x, would be less than 0. So if your first derivative has a value that is less than 0, then the function is decreasing. And if the first derivative has a value that's greater than 0, then your function is increasing. Well, how would we figure all that out? How do we know when something is increasing or decreasing? Well, there's a few things that we're going to do. We're going to recall what partition numbers are in terms of the first derivative. And remember, we talked about partition numbers in section 2.3. We're going to talk about the critical numbers of a function and then the first derivative test. So all of this is going to come together so that we can figure out where a function is increasing or decreasing without looking at a graph, just by being able to find the derivative. So what are partition numbers of the first derivative? So the partition numbers of the first derivative are going to be the x values for which the first derivative is equal to 0, or the x values where the first derivative is undefined. Now, when we find these partition numbers, these x values, they're going to help us determine whether our function is increasing or decreasing on the open interval. They're also going to help us determine local mins and local maxes, which we'll talk about in a little bit. Critical numbers. So what are the critical numbers of a function? The critical numbers of a function are defined as follows. The critical numbers of f of x are the partition numbers of f prime of x. So recall, the partition numbers of f prime of x are places where the first derivative is equal to 0 and places where the first derivative is undefined. So partition numbers that are still in the domain of the function. So a critical number is different from a partition number because it needs to be in the domain of the given function. So now let's put this all together. Let's figure out how to, if I'm given just a function, find the places where the function is increasing and decreasing. We can use the first derivative to determine the intervals where the function is increasing or decreasing and has local extrema. Local extrema we're going to define right here. So how do we figure out where a function is increasing or decreasing or has local extrema? Well, the first thing we want to do is find the first derivative, find f prime of x, and then find the partition numbers for f prime of x. Recall, those are the places where f prime of x is equal to 0 and the x values where f prime of x is undefined. Then what we want to do is place the partition numbers on the number line. This is going to break our number line into sections. Then we select a test value from each one of the intervals we found in step 2 and determine the sign, and by sign I mean positive or negative, of the value of the first derivative at c. If f prime of c is greater than 0, then our function is increasing in that interval. If f prime of c is less than 0, then our function is decreasing in that interval. So local extrema is extreme values, so maximums and minimums. So this is going to be maximums and minimums. So we say that a function goes from increasing to decreasing, you have what's known as a local max. And if a function goes from decreasing to increasing, so from decreasing to increasing, you have a local min. So if a function changes from increasing to decreasing, you have a local max. And if a function changes from decreasing to increasing, you have a local minimum. All right, let's find the intervals of which a function is increasing and decreasing and find the local extrema. In order to do this, if I want to figure out where is this guy increasing and decreasing, what I need to do is I need to do this first derivative test. So step 1 told us that what we had to do was find f prime of x. We have to find the first derivative. So if this is f of x and I want to find the first derivative, f prime of x is going to equal, well, this is 4x cubed minus 12x squared plus 0, and we don't need to write that. Then it says find the partition numbers of x. So this is all within step 1. The first thing we do is find the first derivative and then we find the partition numbers. Now remember, the partition numbers happen in 2 places, where f prime of x is equal to 0 and where f prime of x is undefined. Well, let's look at the second part where f prime of x is undefined first. F prime of x is equal to 4x cubed minus 12x squared. Well, this is a polynomial. Polynomials have domains that are all real numbers, so there's nowhere where it's undefined. Because f prime of x is a polynomial, there's nowhere it's going to be undefined, so we're not going to get any x values for that. In order to figure out where the first derivative is equal to 0, what we need to do is set that first derivative equal to 0 and solve for x. So here, if I were to factor out a 4x squared, the greatest common factor, I'd be left with an x minus 3. If I solve both of these, I have 4x squared is equal to 0 and x minus 3 is equal to 0. Dividing here by 4, I get x squared is equal to 0. Taking the square root of both sides to solve this, I end up with x is equal to 0. And I don't write plus or minus because 0 is neither positive nor negative. For my other one, if I add 3 to both sides, I get x is equal to 3. So my partition numbers are x equals 0 and x equals 3. Step 2 is asking us to place our partition numbers on a number line. So here's our number line. We have 2 partition numbers, 0 and 3. And it says that this is going to break us up into sections. So for step 3, what we want to do is we actually want to choose a test value from each one of those sections. So this is the section from negative infinity to 0. So a number between negative infinity and 0 is negative 1. And then this is the section from 0 to 3. So a number between 0 and 3 is positive 1. And this is the section from 3 to positive infinity. So a number between 3 and positive infinity is 4. So step 3, choose a test value, and then figure out what's the sign of the first derivative for each one of those test values. So what we need to figure out is, what is f prime of negative 1 equal to, what is f prime of positive 1 equal to, and what is f prime of positive 4 equal to. So let's grab a calculator to figure that out. We're plugging in negative 1 everywhere there's an x in my first derivative, which is my 4x cubed minus 12x squared. So 4 times negative 1 to the third minus 12 times negative 1 squared gives me negative 16. So I'm going to write a minus sign to let me know that in this interval, all of my answers are negative. Now let's figure out what happens for f prime of 1. So same thing, the first thing that we want to do is plug it into that first derivative, which is 4 times 1 to the third minus 12 times 1 squared. And we end up with negative 8. So this is a negative number. I'm just going to write a minus sign because, again, it told us to determine the sign, positive or negative, of the first derivative, which means that here all these numbers are negative. Finally, let's find f prime of 4. So f prime of 4, again, grabbing our calculator, we would have 4 times 4 to the third minus 12 times 4 squared. And we end up with positive 64. Well, 64 is a positive number, so that means that every number in this interval would be positive. So step 3 said select a test value from each interval found in step 2 and determine the sign, positive or negative, of the first derivative in that interval. And then it says, hey, anywhere where your first derivative is greater than 0, which means you're positive, your function is increasing. And anywhere where your first derivative is less than 0, which is your negative, means your function is decreasing. So what does that mean for us? Well, it means that in this interval, we are decreasing because here we were negative, we were less than 0. And in this interval, we are also decreasing because we were less than 0. And here, our function is increasing because we are positive or we are greater than 0. So if I want to know where f of x is increasing, I would say it's increasing from the interval from 3 to infinity. And f of x is decreasing from the interval from negative infinity to 0 and then 0 to 3. So it's going to be decreasing from all of these values. So we would say it is decreasing from negative infinity all the way to 3. The last thing it's asking us to find here in this example is it's asking us to determine what the local extrema is. So we need to figure out what's our local extrema. Well, our local extrema is our maximums and minimums. And how do we find maximums and minimums? Well, we said if your function goes from increasing to decreasing, you have a max. And if your function goes from decreasing to increasing, you have a min. So here, our function went from decreasing to decreasing some more. Well, if I don't change from increasing to decreasing, I'm not going to have local extrema at that x value. But here I went from decreasing to increasing. Well, if you go from decreasing to increasing, you have what's known as a minimum value. So for this function, f of x has a local min at the point, well, the x value of my point is 3. To find the y value of my point, I'm going to have to plug 3 back into the original f of x. So I'm going to have to plug 3 back into the original f of x. So if we grab a calculator here, plugging it back into the original f of x, I'm going to have 3 to the 4th minus 4 times 3 cubed plus 10. So if I want to figure out where I'm having a local min or max, I have to plug that x value back into the original function. In this case, it's going to be 3 to the 4th minus 4 times 3 cubed plus 10. I'd hit enter and I get negative 17. So I have a local minimum value at 3 comma negative 17. If we were to look at a graph of this function, so in Desmos, I'm going to say y equals x to the 4th minus 4x to the 3rd plus 10. And I notice here that my function is decreasing and then continues to decrease all the way till it gets to negative 3. And this minimum value is at 3 comma negative 17. And then it starts increasing again. So our function was, again, decreasing from negative infinity to 3, increasing from 3 to infinity, and has a local min at 3 comma negative 17.